Hello everybody, welcome to my YouTube channel. Today I'm going to talk about Conconi test. So the goal of this video is to make this plot and to evaluate this plot basically. What is Conconi test? So the Conconi test is endurance test to measure anaerobic threshold and maximum heart rate, and this test is maximal test, which means that you have to execute this test until exhaustion, and you have to manipulate the speed while you are running. Basically, you have to increase the speed every 200 meters. I'm gonna explain the procedure in detail right along, and while you are running, you have to record your heart rate. What can you do with the result? As you saw on the plot, you can find the anaerobic threshold, and by using the anaerobic threshold you can find your training zones, for example. So this is a plot that you saw it on the previous slides. The red line represents the anaerobic threshold, which is around 180 beat per minute or speed of 10 km/h. So anaerobic threshold is basically the point you switch metabolism from aerobic to anaerobic. As an example, marathoners use this threshold because if they increase pace more than 180 beat per minute, they get tired very soon, so they cannot keep running for a long time for long distance. Marathoners usually keep their pace below their threshold. Or during the training, you can manipulate the intensities by using this threshold concept. As you can see, you can find 95%, 90%, 80% of this threshold. If you are tired or after intensive exercise, you can basically decrease training intensity to maybe like 180 beat per minute. Or if you feel super good, you can train around anaerobic threshold, which is 180, or maybe like a 30 rest 175 to increase your endurance capacities. Tools you need. So you can use track, treadmill, or cycle ergometer. Totally depends on what's available for you. So if you want to use track, it doesn't really matter. You use a 200 meter, 400 meter track. You need a pacer on the cones. Pacer, for example, beeps. I'm gonna explain how you use pacer on the cones. Beeps on the cones. You put cones every 20 meters on the truck, and you listen to the beep by speaker or headphones or earphones or whatever. And every beep you have to reach to 20 meter cone. Next beep, next 20 meter cone, next beep, next 20 meter cone. And the beep is consistent every 200 meters. So like I said, you have to control the speed, and the speed increases every 200 meters. I'm gonna explain the procedure later on, but that's how that works. So beep is consistent until next 200 meters. So if you just follow the beep and reach into the appropriate cone every time, you actually keep the speed consistent. But if you just use treadmill or cycle ergometer, you don't really have to use a pace on the cones, because you can find your distance running and speed on the screen attached to the treadmill or cycle ergometer. So every 200 meters you just press the bottom to increase the speed basically. So maybe that's easier for you. And while you are running, you have to monitor your heart rate. You can use Porter, Garmin, whatever it's available for you. Then as I said, you can use a speaker or earphones to listen to the beeps. Procedure. So first of all, you have to define starting velocity or starting speed. If you are untrained, you can start with 7 km/h. if you're trained or former athlete, you can start with 8 km per hour. If you're a really good athlete, you can start with 12 km per hour. It totally depends on your status. And like I said, you have to manipulate the speed or increase speed 0.5 km per hour in every 200 meters. And this is a maximum test, so you have to run until exhaustion or as much as you can. Okay, so I explained kind of everything, and you may wonder what's next. So like I promised, I'm gonna explain how to make a beep, because you probably cannot find appropriate beat for you, because like I said, you have to put the cones if you use a truck, and it totally depends on like the distance you put the cones, like 20 meter for 40 meter, but you have to manipulate the beep, right? So I'm gonna explain how to customize the beep, and of course you have to define the starting velocity, 7 km per hour, 8 km per hour, 12 km per hour. It totally depends on your status, so you have to customize the beep anyway. So I'm gonna explain how to do it by using MATLAB, but maybe some of you don't have access to MATLAB, so I will put several types of beeps on YouTube. So yeah, you have tools, you know the procedures, and you collect the data. Then you wonder what's next. How are you gonna make a plot? How are you gonna analyze the data? Don't worry, I'm gonna explain how to make it by using MATLAB again. But also I'm gonna explain how to find an aerobic threshold and a training zone by using Spreadsheet as well. So let's check it out. Okay, so MATLAB. So MATLAB, as I say, is a programming language, and you can make a code for anything, I have to say. But like for this time, I'm gonna use MATLAB programming language to make a beep. So first line is a frequency equal 1500. It could be anything, but like how frequency works is the higher the frequency, the higher the key, and the lower the frequency, the lower the key, or like a deeper sound. So that's how it works. It doesn't have to be 1500. You can play around. It can be like 1000, it can be like 100, anything. And the starting velocity is the second line, and I just put it 8. It represents like kilometer per hour. If you remember, like you can put 7 if you're untrained. You can put 12 if you're a really good athlete. It totally depends on your status. And the third line is another frequency. So the first frequency is for the every 200 meter, and this second frequency is for every 20 meter. So beeps within 200 meter. So what I wanna do is like it's like a shuttle run. So you hear like a beeps within one run, right? Like from starting point to the turning point, you hear some beeps, maybe like from like a deeper sound to like a higher sound, higher tone sound, and then at the turning point you hear like a distinctive sound. So basically it's kind of the same thing. You hear like a one distinct sound every 200 meter, and within the 200 meter you hear sound for the pace control. AMP is the amplitude. It defines the loudness of the sound. It can be any number. I just put it 10. And the pause for 5 seconds. This is not really necessary. I just put it because probably I just need 5 seconds to prepare recording these beeps later on. So just put it 5 second pause here. If you don't want it, you just remove it. And the next code is like a while loop. Just put while loop infinity times because I don't know how many laps you can run. Then I define the variable called speed. This is meter per second supposed to be. Why I have to change it to meter per second from kilometer per hour? Because probably easier because you use 200 meter lap, and you have to increase speed by 0.5 kilometer per hour later on, but to just find or compute like a lap time or like a rate of power, so like converting meter per second, probably easier. But you can keep kilometer per hour if you want, but in this code I just created this line to convert from kilometer per hour to meter per second. And then, as I said, I defined the lap time by dividing 200 meter by time or speed, kilometer per hour. Then, as you imagine, you get lap time in seconds. Then I create a pulse because I have to define the pulse between beeps, and you need 10 pulses because I want beeps for every 20 meters. So there are 10 20 meters within 200 meters, right? So I just need 10 pulses, which means I need 9 beeps within 200 meters. Then you get to the point the beeps actually created. So this is like a sound function. Sound function, it needs sound vectors. So to create the sound vectors, I created the function called the tone here. This here. You just need to put the desired duration, frequency, and amplitude, and it creates sound vectors. And the formula is here. Probably you can find this formula online, but I'm gonna put this function on the old MATLAB code on my blog, so you just download it, copy it, play around. Then I put 0.25 duration and the frequency is here, like a 1500, and the amplitude is 10. So this is the beep for every 200 meters, and I make it kind of distinct because duration is 0.25 and the frequency is 1500, and you see later on this is kind of distinct because I used 0.1 duration for the within beeps, within 200 meter beeps, and the frequency is just 100 here. It's very distinct. And then you reach to the point you create within 200 meter beeps. So as I defined pulse, this is a fast pulse after the beep of 200 meter point. Then you have sound function again, and this is, like I said, like within 200 meter beeps. So 0.1 second duration, and the frequency starting from 100, and the amplitude is the same, 10. And every loop frequency increases by 100. So first beep is frequency of 100, second beep is frequency of 200, and so on. So which means you increase the frequency, so the beep tone of the sound increases. So it's the tone getting higher. So I'm gonna run this code and you hear the sound later on, so you get what I mean later on. And yeah, of course, every loop there is a pulse here, and after 9 loops you get another pulse, so 9 pulse and 1 pulse, so it creates 10 pulse. Right on. And then I'm gonna reset the frequency to 100, right? So next lap, next 200 meters, you just repeat what's there in the first 200 meters. So it doesn't start from for example like a 900 frequency, but it starts from 100 frequency again in the next 200 meters, if that makes sense. And starting velocity was 8 for this time, and increases by 0.5. So next loop is 8.5, and next loop is 9, next loop 9.5, and so on, so on. Okay, so I think I explained everything, so I just run this code. So this is the starting beep, so you start running. So right now you're running, and you reach the first 20-meter point or cone. You keep running, and you reach to the next point, like a 20-meter point. Yes, and the next 20-meter point. And as you hear, the sound, like a tone, is getting higher, right? So that's what I mean, increasing the frequency by 100. So as I say, this is customizable, so you can manipulate starting velocity here, as I said, or even like you can manipulate the sound of beeps. And of course, I set it as like a beeps for like each 20 meter, but like you can like customize the beeps for each 40 meter, for example. So there are only 5 40 meters within the 200 meter rep, so you just need to define the pulse. So this should be 5 instead of 10, because you only need 5 pulses. Then this loop, you only need like 4 loops instead of 9, because 4 beep sounds within 200 meter, because 5 pulses and 4 beeps. If you wanna change the like frequency of beeps within the 200 meter to each 40 meter, basically. So it's very flexible. You can play around, and yeah, like I said, I'm gonna put this code and the function on my blog, so you can download it, you can play around. Now you have everything you need. You have all tools, including beeps, and you know the procedures, so you are ready to go to the field and collect the data. Okay, come back to the MATLAB. So after you enjoy the concurrent test and you got all data you need to Unwrite. So as I explained, or like as I mentioned, I'm gonna show you how to analyze the data by using MATLAB and the spreadsheet in both ways. So, but I'm gonna do the MATLAB first. So I just imported the data from Portal Cloud, because I used the portal to collect my heart rate data, and I'm just gonna save the data into variable called data here. So let's take a look at what's inside. You have so many variables, but like for this analysis, I only need time, heart rate, and distance variable. To be honest, you can use either time or distance variable to analyze the data, either one. But since I have both, I can show you in both ways. So let's take a look at the overview of my heart rate over time. Okay, like this. As you see, it's very tough to find a deflection point or like a Narvik threshold by just taking a look at this overview plot, right? so that's why I have to extract some meaningful data points. So that's why I have to use the distance or time variable. So basically this loop find the index of the 200 meter point. So let's take a look at it. Okay. So index number of 92. Let's take a look at what's the value of distance in 92nd index. Here we go, it's just right above 200 meter point. Then what I'm gonna do is extract the heart rate value here. Then I'm gonna do the same thing for the next 200 point, which is like a 400 meter, and take the heart rate value and the 6 meter point, take heart rate value, and so on. And the principle is the same for the time. I'm just gonna define the time which is supposed to take in each 200 meter. Then I'm just gonna calculate the accumulated lap time. So this for loop, again, I'm just gonna convert velocity, like a kilometer per hour, to meter per second. Then I'm gonna calculate the lap time, and I can know the total lap time. And just by adding, I get accumulated total lap time in seconds, right? Then every loop I'm gonna increase the velocity by 0.5 kilometer per hour. But again, I'm just gonna convert from kilometer per hour to meter per second. Then I'm gonna convert time format to second, because in this data, this time format is not in second. So I'm just gonna convert time format into second, because I just defined the accumulated total lap time in second. Then basically it's the same thing, just need to find the index, corresponding index right above whatever times it's supposed to take for every 200 meter. Let's see. Okay, so this is the index point defined by time, and this is the distance. The index point difference is just only, it's not exactly the same, but I could just, I would say, minor difference. So we can use both ways technically. So I just stick to the time variable, or like index point defined by time. So it just need to find the corresponding heart rate. So this is heart rate, this is index. So I can find all heart rate corresponding to this index. And for the beta looking, I just reconvert the speed unit from meter per second to kilometer per hour. Then let's see this plot. Here we go. So kilometer per hour looks better, I guess. And the y-axis is the heart rate, beat per minute. So every point is every 200 meter. So I started from 8 kilometer per hour. So obviously this is 8 in x-axis, and y-axis is 154. So at the point of the first 200 meter, my heart rate was 154. And for the second point, 159 and 173, and so on. And what you have to do with this plot is to find the deflection point, which is very subjectively, and maybe you need some experience, but I feel like this is the point the increment of heart rate decrease a little bit. You see, this is like imaginary linear line, suddenly decrease a little bit. This is sometimes by chance. Some data you can find easily the diffraction point, but like there is some data point or like some data there is no diffraction point. So sometimes it's just by chance. But yeah, for this analysis, fortunately, I got some diffraction point, or a candidate of a diffraction point, I would say. So what I'm gonna do next is try to find a linear model of first 6 and the rest of the point separately. Okay, so as I said, first of all, I want to make sure the correlation between the speed and heart rate only for the first 6 data points. Find this. Okay, and correlation coefficient is 95, which is I think pretty high. Let's do the p-value. Okay, it's less than 0.05, so we can reject the null hypothesis, which is speed and the heart rate. It's not correlated. We reject that. Then I'm gonna make a linear model by using fit LM. So basically, input is the same as I did for the correlation, and I'm just gonna use a predict value, predict function to predict my heart rate of this range from 8 km per hour to 12 km per hour. So you may wonder why I have to extend the linear model a little bit, because if I want to make a linear model, I only need range from 8 to 11, no, 10.5 here, but I defined until 12. Let's take a look at the video first. Actually, so this green linear line is from this linear model, linear arrow here. Then I'm gonna do the same thing for the rest of the points, like from 7th to 11th data point. And I'm gonna do the same thing for correlation, find or like create a linear model. And again, you have to extend the prediction range a little bit to find this closing point. Because if you only define a linear line like which is from 11 km per hour to like 13 km per hour, the line stops here. But I want to extend the line to find the crossing point, which is right here, and this is the greater point of anaerobic threshold, which is one of our goals. Then after you define the linear model, you just need to do little algebra. I'm just going to use system of linear equation. So this first equation is linear line, and this is for the second linear line. And if you want to find this common x, transform the two equations a little bit to this equation. So basically, you just need to find the coefficient of a1, a2, b2, b1. How you do that? You just use the dot function here. You just put the name of the linear model. You just put the dot, and you just type coefficient dot estimate, and there are two coefficients because b1 and a1, for example, and 1 is intersection, which is a1, and 2 is slope. Then you just put corresponding poles to this equation. Then once you know the anaerobic threshold in terms of like speed, like a kilometer per hour, you can just use the predict function to find the corresponding heart rate. So in this case, anaerobic threshold is around 10, and anaerobic analytic threshold heart rate is around 180. Let's check it out. Crossing point here, it's around 10 km per hour, and the heart rate is at 180. So it's successful. And then after that, based on the analytic threshold, you can find training zones, which is whatever you want, like 95%, 90%, 80%, 65%. Basically, you just multiply analytic threshold in speed with 0.95 or 0.9 or 0.8 or something like that. And then you use the predict function to predict your corresponding heart rate, like 95% of corresponding heart rate. I'm gonna run this. Then at last, I'm just gonna plot the data, or the old data we got, and this is exactly the same plot I showed you on the slide. And pretty much it. So I'm gonna explain how to analyze data in Spreadsheet. Let's check it out. Okay, so Spreadsheet. So I just created a Conconi test sheet, and all you have to do is you just plug in your data into this sheet. So for example, you started from 7 km per hour, and you just put corresponding heart rate here, and just put it all the way until you get all the way until the point you got exploded. And this is example data which I showed you in the MATLAB. So I started from 8 km per hour, and my corresponding heart rate is 154, and for next point 159 and 173 and so on, and then I stopped 13 km per hour, which is 11 left, right? Yes. Yeah, so you just plug in the data and you just plot. Just to make a plot. Yes, direct. I want scatter plot like this, and you want to fix the dimension a little bit because it's really tough to find the deflection point. By looking at this, so 150 and the 210 is fine. So okay, so I'll find a deflection point. So maybe right here, as I showed you in the MATLAB, because increment of heart rate probably decrease from the point here, like this imaginary linear line, maybe like this going here, but decreases somehow from here. So I would say this is a deflection point. So I only count first 6 as a first linear model, and the rest of the point as second linear model. So I'm gonna do pretty much the same thing. So first of all, you have to define the slope and the intercept of the first linear model, or like first 6 points. So you just use function slope, right? And then you just plug in the corresponding or like first 6 points. Be careful, you have to put the y-axis first, which is heart rate value first, and then speed. And do the same thing for the intercept function. Input is the same. And for the second linear model, you just put the rest of the points here. And you do the same thing for the intercept here. Then you use algebra or like system of linear equation to find the common x between two linear model. or you just plug in the value into this formula, intercept like A1, A2, and B1, no B2, and B1 here to get the common x 10, and you just use the first linear model, so slope times whatever speed here plus intercept here. So 10 km per hour and 180 beats per minute is exactly what we find, or like what I found in MATLAB. Then you're gonna find 90% of anaerobic threshold as the training zone. So pretty much the same. What you're gonna do is find the 90% value of this anaerobic threshold in speed. Then again, you just plug into the formula of the linear line, or like the first linear line, or like a linear model. So basically the same thing, slope times speed plus intercept. Then you get 169 basically beats per minute. So this is like 90% of your anaerobic threshold, and you can use it as a training control. If you want to find 95% of anaerobic threshold, you can just change the value here, 0.95 instead of 0.9, and you can find 95% of anaerobic threshold. And you can play around, obviously, and I'm gonna put this file on my blog, so you can just download it, copy and paste, and play around, and you can find training on easy without using MATLAB. Okay, come back to the presentation slide again. So before you evaluate your result, there are some considerations you have to take into account, which is you have to have at least 8 points with correlation coefficient more than 0.98. So if you take a look at the plot again, I only have 1, 2, 3, 4, 5, 6 data points before anaerobic threshold, so I couldn't meet the criteria. And also, if you remember, R value was less than 0.98, so I couldn't really meet this criteria in both ways, like 8 points and correlation coefficient. Anyway, and next consideration is I have to have at least 3 data points after anaerobic threshold, which I had, and I think I got 5 data points after deflection point, so I could meet this criteria. And the last criteria is maximum increase of heart rate should be, or must be, less than 8 beats per minute. So if you look at the plot, probably this gap here from second data point to third data point, the gap is more than 8 beats per minute, so I couldn't meet this last criteria, unfortunately. Maybe what I'm gonna do next is redo the Conconi test. Maybe the reason why I couldn't get to at least 8 points is because I overestimated my status. I started from 8 km per hour because I used to be an athlete, so I started from 8 km per hour, but probably I should have started from 7 km per hour instead of 8 km per hour. So maybe next time I'm gonna do the Conconi test with 7 km per hour as a starting velocity, so hopefully I get more than 8 points before the deflection point, and I get correlation coefficient more than 0.98. And for the maximum increase of heart rate, I got, I think, one gap which was more than 8 beats per minute. It was between second and third data point, which was beginning of the Conconi test. Reason why I had a huge gap between second and third, because of broad loading from vein to artery. As far as I remember, I kind of skipped warming up, so my broad was shifting from vein to artery. I'm not gonna explain that phenomena in details in this video, but maybe like another video I'm gonna explain oxygen kinematics, another interesting topic to talk about. Maybe another video. Sorry about that. And one tip I can show you is like anaerobic threshold might be around 85% of maximum heart rate. So you find the maximum heart rate in the data from Conconi test you get, and you just compare the value with anaerobic threshold that you found from the plot. Then if there is a huge gap between two values, you have to maybe resync or like reconsider or like re-analyze or even redo the Conconi test. But if it's close enough, maybe it's valid anaerobic threshold. So that's one tip, you can find the appropriate anaerobic threshold. Okay, that's it. And thank you for watching my video, and hope you enjoy my video, and see you next time.